Today we're going to take graphing functions into the real world. We're going to model real world problems with linear functions and graphs. So let's start with just remembering that there are really five, actually six, if we were to put those mapping diagrams in here, ways to represent functions. So we've talked about function rules. We've talked about making a table. Remember the fav4, they don't have a negative here, but using a table to make a set of points, set of ordered pairs, and plotting them. We've gone from the equation to the table to the graph. That's kind of what we've been working on. Today we're going to put the words up front, and the words are going to be not so much just about math, but more about the real world situation. We're going to today have the function given to us. We're going to make a table. We're going to graph a real world graph. Now, I'm going to caution you, when we go to graph that real world graph today, we're not really going to be using the coordinate graph paper with the four quadrants, quadrant 1, quadrant 2, quadrant 3, and quadrant 4, because oftentimes, matter of fact, most of the time in the real world, we're really not dealing with negatives. So we're going to go to regular graph paper and really just be graphing on quadrant 1, the all positive quadrant. So we're going to go forward and kind of look at taking words, making a function rule, using that function rule to make a table, and then graphing that table of values. So remember that words are going to be one or more sentences that describe a relationship between variables. So that's going to be verbal. That's going to be an English sentence. Then we're going to write an equation, a function rule, and that function rule is an equation that shows how those variables are related. That's going to be an algebraic representation. We're then going to make a table of values. You know, you could do a set of ordered pairs, but we all seem to like that table idea. Remember that your book sometimes makes the table going down vertically, and sometimes it makes it going horizontally. I prefer it going down, but just realize sometimes the book will do it either way. And a table will identify specific input and output values for the function. That will be a numerical representation. And to be honest, we've been using those fav4 or fav5, depending on, how many spaces we have. But today you're going to notice that we're not going to start with -2 or -1. We're going to usually start with 0 because you can't have negative days or negative time. So we're really going to be focusing on positives, which will make you happy, makes it a little bit easier. And then once we have our table, we're going to do a graph. And we're going to talk today about setting up the graph. Setting up the graph before we plot the points today will be the thing that takes the most time. So I'm going to start with a real world example. It's on page 295. So I'd like you, if you need to, pause this right now and grab your book, please do. So the first example is a Lockheed SR-71 Blackbird jet that has a top speed of 36.6 miles per, please notice this, minute, not per hour. If I take that 36.6 and multiply it by 60 minutes in an hour, that jet is flying at 2,196 miles per hour. If X, we're going to, have two variables again in our function rule. And in this case, look at, we got miles and we've got minutes. Those are going to be our two variables. Now, X is going to represent the number of minutes. If time is involved, it's usually your independent, it's usually X. And the miles traveled is going to be your Y. You're going to see right here, I'm defining the variables in kind of a nice, concise way. When you write a function rule and it's got variables in there, you always tell everybody what those variables stand for. So in this function rule, the input would be the number of minutes that the jet is flying, and the dependent variable Y that's waiting for the math to happen will be the miles traveled. So if this jet was to fly for 1 minute, 36.6 times 1 would be 36.6. So for 1 minute, there would be 36.6 miles traveled. I mean, that's almost from Ledyard to Hartford in one, in 1 minute. So now what we're going to do is we're going to make a function table, and we're going to be using this rule. And we're not going to get worried about the decimal. We're going to multiply using our calculator, and we're going to put an input of 2 minutes, 3 minutes, and 4 minutes. So notice that we're not using negative inputs because it wouldn't make sense to put in -2 minutes flight time, okay? So I'm going to ask, the video is going to pause. I'm going to ask you to put 36.6 times 2. What is that output? And then write what the point would be. Do it for 3 minutes and do it for 4. Okay, so let's see how you did. So here, 36.6 times 2, right? Let me just actually get rid of this guy. He's not going anywhere. There we go. 36.2 would be 73.2. So for 2 minutes, the jet covered 73.2 miles. 36.6 times 3 would be 109.8. So for 3 minutes, the jet covered 109.8 miles. And for 4, it would be 146.4. And that's really from Ledyard to New York it's a little bit less than that. So in 4 minutes, that jet is past New York City if it took off from Ledyard. Pretty amazing stuff. So now what we need to do is graph this. So are you okay making the table? It's kind of the same idea we did. We put in some inputs, we do the math, we input and do the math, and now we're going to plot these points. Now don't get scared by the fact it's 36.6 or 109.8. We're going to it's an eyeball, it's a guesstimate as we plot those points. Okay, let's talk about graphing this one. So, the first thing in your book is lousy at this. Make sure you put a title. So I put SR 71 distance. Remember that when we defined our variables, for this rule, X was the number of minutes, Y is the miles traveled. Those are your labels on the axes. So there's the minutes, there's the distance traveled in miles. Now notice we're not using the coordinate graph paper. As I mentioned a minute ago, there's no point to have quadrant 2, 3, or 4 because we're not going to talk about negative minutes or negative distance. So we're only using quadrant 1. So we're going to use regular graph paper. We're going to draw a y-axis connected to an x-axis. And here is sort of the toughest part. What numbers do you put and where on the two axes? So basically, you look at your axis, and for a table, we're only going up to 4. So on this axis, notice I'm using basically 2 blocks for 1 minute. So each block is a half a minute. So 2 blocks for 1, then another minute, 2 blocks, another minute, 3, would be to 3 blocks and so forth. Now, when I go this direction, I have to make sure I get up to at least, say, 150. And if I want to make predictions, I want to even go up a little further. So if I was to go by tens, I wouldn't make it. I wouldn't reach call that 150. So notice I'm going by 20s. So 20, 40, 60, 80. Every block has to have the same number of miles going up. You wouldn't go from 20 and then to 60 and then to 80 and then to 140. Like each block here represents 20. Now, please, please, please listen. When you're picking scales like 3, 7, 11 are horrible numbers to pick. When we're picking numbers, if we can't go by ones, going by 2s, 5s, 10s, 20s, 25, things like that. But really, it's horrible to go like 3, 6, 9. They're horrible to graph, horrible to read. So notice that we're picking either a 1-to-1 or by 10s, by 20s, easy numbers for the eye to read and to plot. Now, once you've set this up, we need to plot the points. When we go to plot those points, notice I'm going to plot 1, so that's easy, 1 in the x direction, and I have to go up 36.6. This is going to be an estimate. It's not going to be like, in the crosshairs of a vertical and horizontal line. So 20, halfway up would be 30, and then halfway from that distance to 40 would be 35. So I'm thinking it's right about there. The next one would be 2. 73.2, right? So let's find 70, 20, 40, 60, 70, and a little bit more. Are you with me? The next one is going to be 3 minutes and about 110. So 20, 80, 100, halfway would be about 110. Do you see my points falling in a line? This is a linear function, okay? So they should be falling in a line, which will also help you place the points as you get further out there. And then 4 minutes and like about 150, 140, 150, and then back off a little bit. And again, looking at that line right about there. I'm now going to pick up my ruler and I am going to put in a line to, actually it'll be a ray because it's not going to have an arrow pointing this direction because you don't want to go into the negatives. And I'm going to go ahead and draw that in. And there is the graph of this function rule. Okay, so let's just, now try to do one together. So remember that the situation is going to be provided in words. You have to decide who is independent and dependent. So who is the X and who is the Y. Input values will be chosen based on the situation, and negative numbers don't always make sense unless you're talking about like going underwater or losing money, something like that. But most of the time, we're all positive. On the graph, we're going to make sure we put a title. The labels will come off our definition, the X and the Y. And then you're going to make sure that your scales fit the data and that they are the same amount going left to right and going up. And then I'm going to introduce a word called continuous and discrete. Now, before we move on, remember, we've kind of done this already. We talked about taking a function rule. We talked about putting inputs. So the opposite of -2 would be 2, plus 2 is 4. The opposite of -1 would be 1, plus 2 is 3. The opposite of 0 is 0, plus 2 is 2. Opposite of 1, -1 plus 2 is 1. And the opposite of 2 plus 2, -2 plus 2 is 0. We plotted the points and we drew the line in with arrows. So we know how to go from a rule to a table to a graph. The only thing that's different today is we're not using the negatives. So quadrant 2, 3, and 4, we're just looking at quadrant 1, and we have to set those scales. So we're going to use regular graph paper, and we just have a little bit more work to do kind of as we go forward. All righty. So let us do one example start to finish together. And then when you come into class, we'll do another one, and then we'll practice. So let's say that Ava's grandmother is starting a savings account for college, and she gives Ava an initial deposit. So here, Ava, it's $500. So as time starts, she goes to the bank, she puts $500 in. And then every month, the first of the month, she's going to add 100. Now, I am giving you the function rule right here. Pretty soon, you're going to have to write that from words, but notice that that 500 happened once. So see how the 500 is not attached to the variable. It's a constant. It doesn't change. And then we're adding to it 100 times X. What is X? X is the number of months. So 1 month, you're going to add 100. 2 months, you're going to add 100 times 2 or 200. 3 months, you're going to add 100 times 3 or 300. And what is the Y? Well, he's the dependent variable. He's waiting for the math to happen each month. He's going to be the total amount in the account every time you add that extra 100. So we're going to make a table, and then we're going to make a graph. And we want it to cover several months. So we're not just going to put like, 0, 1, 2, 3. We're going to try to get out in time to see how this money is growing. So these are your choices. Now, the first thing I'm going to recommend, though, is that you always put in 0 as one of your inputs, rather, as long as it's allowed, because that'll anchor your graph to the y-axis. So if we put 0 in here, 100 times 0 is 0 plus 500. That's our initial amount. And you'll see when we plot that point that our graph will start on the y-axis. Now, the next one I didn't put in was 1. I'm just picking numbers. So I'm going to do 3, I'm going to do 8, I'm going to do 18 and 30. Now, these are not the only numbers you could pick. You could have picked 0, 5, 10, 15, and 20. I just picked these to let you know that you choose the inputs. And the fave 5 or fave 4 are no longer going to be used because those negatives don't make sense for months, okay? So then I put the 3 in. 100 times 3 is 300 plus 5 is 800. And remember that now, as the numbers get bigger, the calculator is very useful. 100 times 8 is 800 plus 5 is 1,300. 18 times 100 would be 1,800 plus 5 would be 2,300. Her account's growing nicely. And 100 times 30 would be 3,000, and the 500 would be 3,500. So you could have a table that, and should and would have a table that looks a lot different than mine because you might pick different outputs, but just make sure you're not just picking, like for a few months. Several months, we want to get out past, just a few months. Now it's time to graph this. So here are the things we need to do. We need to put a title on. Book is horrible at this, okay? Be smarter than the book. Remember that independent variable, in this case, it is the number of months, will be on the x-axis, and your dependent would be on the y-axis. In this case, it's the total in the account, the total money in the account. You're going to label, and if there are units like months, dollars, that should be part of your label. So don't just put time. Like what time? Seconds, days, years, decades? So make sure you put your units. And also, when you're talking about money, you want that dollar sign, because in a global society, are you talking about US dollars? Are you talking about European euros? What are we talking about? The proper scales, this is going to take the most time figuring out what scales you want to put on the X and Y. You look at your minimum and maximum values in the table to make sure they're covered, and then go from there. And then make sure your intervals are easy to plot and read. Don't use numbers like 3 or 7 or 9. You're going to use numbers like 1s, 2s, 5s, 10s, 20s, 25, 100, 1000, things like that. And then you plot the points, and then you connect and extend. Okay, so let's take a look. Remember that we're doing the grandmas. This is the one we're going to graph, and I'm going to step you through those rules. First thing, I need a title. So I decided to call this graph, once I get there, Ava's College Savings. Okay. The next thing I need to do is put my labels. So remember, in this case, the dollars depends on the months. Like the calendar isn't going to say, oh, look, Ava has $800, so it must be February. The month doesn't depend on the money. The money depends on the month. So your account balance is going to be your Y, waiting for the math to happen, and the months would be your X. So I'm going to put those labels on. Okay. And notice I put the dollar sign there, and notice this says months, not time. Okay, then once I've got those things labeled with units in the right spot, I now need to create proper scales. So let's look at the months. I'm going to start at 0, and I need to get up to at least 30. Now, I only have 10 blocks here, so I can't go by ones. I'll never get to the 30. Remember, we're not going to go by 3s or 6s or anything like that. We're going to go by nice numbers. So I'm going to start at 0, but I'm going to make each block be 5. So 5, 10, 15, 20, 25, 30. And notice I don't have to write the number on each one. Of course you can if it helps you, but I needed to get up to at least 30, and notice my graph does. By putting a little bit more out here, I'll be able to make predictions, which is kind of the whole point of this. Okay, now we've got to go over here and look at what number is going to go on each of these blocks going up. So now as we look, we have to go from 500 to at least 3,500. And again, I'd like to have some extra up here so that I can extend and kind of make predictions. So if I was to go by hundreds, I'm only going to get up to 1,000. Are you with me? So I chose to go by 1,000, actually 500 each block. So 500, 1,000, 1,500, 2,000, 2,500, 3,000, 3,500, 4,000. You don't have to write the numbers on each one, but if you find yourself messing up, feel free to do it. Okay. Now, once I've got that, I'm going to head to plotting these points. So the first point would be 0, 500. And remember I said you want to put 0 in because it'll anchor your graph to the y-axis, okay? And then I've got to plot 3. Now this is 5, so 3 would be a little bit less than halfway. 800, a little bit less than 1,000. I now need to plot 8, so this would be 5. 8 would be right about where my cursor is, and I need to go up to 1,300, which would be a little bit less than the 1,500. Are you doing? And now knowing that these should fall in a line will help me sort of guesstimate the remainder here. So 18, and I need to go up to 2,300, a little bit less, right? So probably right around here. Let me drag it away so you can see it. And then finally, I'm going to come out to 30 and up to 3,500. That one's easy to plot because it's in the crosshairs. Ah, and there is our graph. So that is how we set up a real world graph. Now the question is, do I connect these or not? And that's what I'm going to talk about for a little bit here. But I just want to give you a second to kind of look and make sure that you understand what we're doing here. Okay, so we plotted the points. Now the question is, do we connect these and extend, or do we leave them as individual dots? There's two math terms called discrete and continuous. And depending on that is often whether we would connect them or not. So should the data extend in one direction, both directions? We're going to draw a trend line, and do we need an arrow or multiple arrows on each end? So let's talk about that now for a little bit. So in your book on page 298, it uses these two words that I just mentioned. A function can either be continuous or discrete. Continuous means that you would draw a line in, and the function can take on every value in between the points you've used. Discrete data means that you jump, there's space from one to the other. Now I put a couple words in here you might want to put in your book because I think this is an easy way to remember it. But continuous data usually deals with a measurement. So, the depth of a pool, as the water goes in, or how much liquid is in a glass, like measuring that, or weight. Like, you don't jump from 125 pounds and instantly go up to 126. Your weight goes through all the weights in between. So a measurement of length or weight or something like that would be continuous. So then what is discrete? It's a count. So, the number of ounces in a glass would be continuous because as you fill up that glass, all the levels you go through all the levels. But the number of glasses in the cupboard, it goes from 1 and then it jumps to 2. The weight of each chocolate chip in a bag would be a measurement, continuous. But the number of chocolate chips, you would go from 1 to 2 to 3 to 4. Now be careful. Some people will associate discrete that it has to be a whole number, no fractions. But let's talk about shoe size. So if you have a size 8 shoe, the next one is actually 8.5. There's nothing in between. That would still be discrete data, but it does have those half sizes. So basically, if the domain of the function is integers like 1, 2, 3, 4, then the domain, then it would be discrete. If it's all possible numbers, then it would be continuous. So you can kind of just think about whether all numbers are reasonable as part of the domain, and that'll tell you whether it's discrete or continuous. So let me just give you a couple pictures before we go back to Ava to decide what we're going to do there. So discrete data usually involves a count. So like the number of people in a restaurant. So I check it at 10 o'clock and I check it at 11 and I check it at 12. Boom, boom, I'm jumping from the number of people. There wouldn't be numbers in between. There wouldn't be 12.4 people in the restaurant or something like that. So this would be a discrete. It's a count. However, if you were talking about the temperature in that very same restaurant, as the temperature goes, you turn up the heat and the day goes on, it starts to get hotter. It doesn't go from 68 degrees and instantly jump up to 69. It goes through all numbers in between. So temperature, which is a measurement, would be continuous and you would connect the dots basically. So here we go back to Ava. Now, Ava's case, remember, she starts with 500, and then the next month she would jump to 600, and then she jumped to 700, and then she jumped to 800. So is it discrete or continuous? Did you hear my jumping? So this would be discrete. So normally, you would kind of not draw a line in here because we shouldn't be talking about that she would have $821.50 in the account. She would jump up by hundreds. The problem, however, with this graph is see how each block is 5 months and each amount of money is 500. So to get like the month 1, 2, 3, and 4, like we don't want to put all those dots in. We don't want to just keep putting dots. So, we're actually going to put in, I'm going to call it a line, but I'm going to change that in a minute so that we can catch everybody in between. Now, when it comes, should we be putting arrows on here? Ava's money is going to keep going up and up and up and up and up and up. So we should definitely have an arrow pointing up. But should we have an arrow down here pointing in this direction? And the answer should be no, because we're not going to talk about negative months or negative dollars. So it actually won't be a line, it's a ray. A ray has an endpoint and an arrow on the other side. And we will draw the line in to catch all those extra months that we didn't put dots on. So basically, here is the graph of Ava's savings account. Who cares? Well, we can use this graph to make sort of predictions of what's going to happen for Ava. So what was the account balance after 25 months? So let's see, 5, 10, 15, 20. Here's 25 months. You come up and you hit your line. Boom, right there. See it? And if we go over, she's going to have $3,000. How many months is it going to take poor Ava to get to $4,000? Well, now we're going to go up to the 4,000. And we're going to come over and hit our line. And then we're going to come down and see that we hit at 35 months. So we can use this graph to kind of make those kind of predictions, which is really helpful. So if you ever hear people talking about things happening down the road, like climate change, what's the temperature going to be in 50 years? I mean, how are they doing that? It's kind of this idea where they get data and then they extend it out and make predictions based on that trend. So today we've learned how to graph real-world functions. And I want to go back. I'm going to actually go right here because what I need is right up here. So you're going to put a title on your graph, pretty much using regular graph paper, guys. We don't need coordinate because your graph will be immensely tiny because you're only using the first quadrant. You're going to draw in a Y and an X axis. You're going to put a title and labels. And remember, if time is involved, months, days, years, seconds, that usually is your X. And then over here would be whatever is the quantity that's waiting. The math is waiting. It depends on what happens over here. That would be your dependent variable or your Y. Once you've done that, you're going to kind of make your table. When you make your table, make sure to show some times. So don't just go 0, 1, 2, 3, right? So show some times. And then you do what we've done in the past and you insert your inputs, not using the faves, not usually using negatives, right? Get your math, and now we're ready to plot points. But before we do that, there's no way each block is going to be 1, or our piece of graph paper to try to get out to 35,000 would be huge. So we're going to make scales that are even. So 5, 10, 15, 20. You could go by 2s or by 10s, something like that. Notice that the scale here is going by 500, right? But all the way up, it's 500. Once you've got your scale, you plot your points, and then you kind of decide, are you going to leave the points separate or are you going to put a line or ray in? And to be honest, most of the time we put some kind of line or ray in to make predictions, but again, discrete or continuous tells you as to whether you should do that. So we're going to come into class. We're going to do another one from start to finish together where you do it along with me, and then you'll get a chance to practice real-world graphs yourself. So the question of where do we use this stuff is going to be answered now. Hope you guys all have a great day.